Alright, hello everyone. So, we're gonna resume our Stat 113 with finishing up this chi-square test of association. So if you were not here on the Friday before spring break, you might want to check out some of the notes that have been posted on Sakai to do a little catch-up before watching this video. And so the example that we were talking about was we wanted to know if there was an association between race and getting a callback for a job. And so we were working with some real data that was pretty cleverly collected by some researchers who randomly assigned names that were typically associated with a certain race and a certain gender, randomly assigned those names to resumes, sent those resumes out to employers, and then recorded whether or not each resume got a callback. And so we were first just looking at race and receiving a callback, and so we were examining two categorical variables, race and callback, and we kind of went through some of these early steps. We wrote out these hypotheses. The null was that there was no association. The alternative was that there was an association between those two variables. We talked about expected counts, and we ended about here. And so we were able to construct this table of expected counts if there was really no association between race and receiving a callback. From here, it's going to look pretty similar to that chi-square goodness of fit test that we did before our second exam. And so again, we're going to calculate this chi-squared statistic as our observed count minus what would be expected if the null hypothesis were true, squared divided by the expected count. This test is probably the most computational heavy that we'll get. We were going to kind of lead into R with this and just kind of note that it's starting to get a little bit computation heavy, and we would probably want a computer program to help us out with this test. Like I mentioned before break though, we won't be using R just because it's going to be a little bit too difficult for us all to start learning it remotely. And so for this example, we're already set up really well just to calculate this. And so I'm going to flip back to our observed table of counts really quickly. So I'm going to take this 2,278 minus what's expected if the null hypothesis is true. That's what we talked about, how to get that value on last Friday, and then divided by that expected count. I'm just going to repeat this process for the other three cells. Okay, so what a pain. And if you calculate all that out, you should wind up with a chi-square stat of 16.879. In order, excuse me, in order to use this chi-square stat, we need to be able to use StatKey to find an appropriate p-value. And to be able to use StatKey to get the appropriate chi-square distribution, we need to know its degrees of freedom. And so degrees of freedom, these are again just taken as fact. We don't really provide any reasoning for these. It's just the number of categories of the first variable minus 1 times the number of categories of the second variable minus 1. So in this case, it's going to be, since race is either black or white for this example, and callback is either yes or no, degrees of freedom are just going to be 1. And so then we can go to StatKey, and if you click on the chi-square distribution and enter 1 degree of freedom, you should end up with a graph kind of like this. And so I'm going to mark our observed chi-square stat, which is somewhere way over here, the 16.879. Shade the region that's our p-value. We could see that it's really, really tiny. And if you actually use StatKey to get that p-value, it's the same process as it was for the chi-square goodness of fit. It turns out to be very, very small. So coming back to our example, what does this all mean? Well, a small p-value we said in general meant that there was strong evidence for whatever our alternative hypothesis was. In this case, there's going to be strong evidence that race and receiving a callback for a job are associated. And I'm going to throw our chi-square stat that we calculated as well as our p-value in my conclusion. We can also figure out the contribution of each cell to the chi-square statistic. So remember in our calculations here, the contribution of the first cell is just this. The second cell is just going to be that, third cell, and fourth cell. And so each of these contributions, if you calculate them out, are 0.679. And so we see that these two are the reason we have such a large chi-square stat. And really, if you look at the original data, we see that we have a significant result because white applicants tend to receive a callback more often. Okay, and so one last thing that kind of ties in from what we talked about at the very beginning of the semester is that this study was actually an experiment because researchers, they randomly assigned the names to the different resumes. And so because this is an experiment, remember that means that we can conclude causation. So unlike the example that we did earlier with the gender discrimination and Simpson's paradox, in this case, we can say that there is evidence of racial discrimination. So statistics does get used in these social justice cases where there is data that you could use. And so this is just one such example where it can be shown statistically that there is evidence that employers are exhibiting some level of racial discrimination. The handout example that you'll work on later today is much lighter. It just covers the baseball data that we explored about a month and a half ago. In that handout, it says that you'll be given the chi-square stat and in class, and since we are having a non-traditional class, I'm going to provide that here. And so the chi-square stat that you get for that example should be 18.977. That's about it for this test. Excuse me, I'm so sorry. Let me know if you have any questions.